we've looked at the primitive queries and the ways that streams are used to implement the means of combination, right? And or, and not. Now let's go on to the means of abstraction. Remember, the means of abstraction in this language are rules. So Z is a boss in division D. If there's some X who has a job in division D, and Z is the supervisor of X. That's what it means for someone to be a boss. So, and in effect, if you think about what we're doing with relation to this, there's the query we wrote. The job of X is in D, and the supervisor of X is Z. What we in effect want to do is take this whole mess and draw a box around it. And say, this whole thing, right, inside the box is boss of Z in division D. That's in effect what we want to do. So for instance, if we've done that and we want to check whether or not it's true that Ben Bitdiddle is a boss in the computer division. So if I want to say boss of Ben Bitdiddle in the computer division, imagine typing that in as a query to the system. In effect, what we want to do is set up a dictionary here which has Z bound to Ben Bitdiddle and D bound to computer. Right, where'd that dictionary come from? Let's look at the slide for 1 second. That dictionary came from matching the query that said boss of Ben Bitdiddle in computer onto the conclusion of the rule, boss of Z in D. Right, so we match the query to the conclusion of the rule. That gives us a dictionary. And that's the thing that we would now like to put into this whole big thing and process and see if anything comes out the other side. And if anything comes out, right, it'll be true. That's the basic idea. So in general, the way we implement a rule is we match the conclusion of the rule against something we might want to be checked it's true. That match gives us a dictionary, and with respect to that dictionary, we process the body of the rule. Okay? Well, that's really all there is, except for two technical points. Right? The first technical point is that I might have said something else. I might have said, who's a boss in the computer division? So I might say boss of who in computer division. And if I did that, what I would really like to do, in effect, is start up this dictionary with a match that sort of says, well, D is computer, and Z is whatever who is. And our matcher won't quite do that. That's not quite matching a pattern against data. It's matching two patterns and sort of saying, are they consistent or not? Or what ways make them consistent? In other words, what we need is not quite a pattern matcher, but something a little bit more general called a unifier. And a unifier is a slight generalization of a pattern matcher. What a unifier does is take two patterns and say, what's the most general thing you can substitute for the variables in those two patterns to make them satisfy the pattern simultaneously? Let me give you an example. If I have the pattern two-element list, which is X and X. So this says I have a two-element list where both elements are the same, and otherwise I don't care what they are. And I unify that against the pattern that says there's a two-element list, and the first one is A and something and C, and the second one is A and B and Z. Then what the unifier should tell me is, oh yeah, in that dictionary, X has to be A, B, C, and Y has to be B, and Z has to be C. Those are the restrictions I'd have to put on the values of X, Y, and Z to make these two unify. Or in other words, to make this match X and make this match X. So the unifier should be able to deduce that. But the unifier may, right, they're more complicated things. I might have said something a little bit more complicated. I might have said there's a list with two elements, and they're both the same, and they should unify against something of this form. And the unifier should be able to deduce from that, right, that Y would have to be B. Y would have to be B because these two are the same, so Y's got to be B. And V here would have to be A. And Z and W can be anything, but they have to be the same thing. And X would have to be B followed by A followed by whatever W is, or whatever Z is, which is the same. So you see, the unifier somehow has to deduce things to unify these patterns. So you might think there's some kind of magic deduction going on, but there's not. A unifier is basically a very simple modification of a pattern matcher. And if you look in the book, you'll see something like 3 or 4 lines of code added to the pattern matcher you just saw to handle the symmetric case. You remember the pattern matcher has a place where it says, is this variable matching a constant? And if so, it checks in the dictionary. There's only one other clause in the unifier which says, is this variable matching a variable? In which case you go look in the dictionary and see if that's consistent with what's in the dictionary. So all the quote, deduction that's in this language, if you sort of look at it, sort of sits in the rule applications, which, if you look at that, sits in the unifier, which, if you look at that under a microscope, sits essentially in the pattern matcher. There's no magic at all going on in there. And the quote, deduction that you see is just the fact that there's this recursion, which is unwinding the matches bit by bit. So it looks like this thing is being very clever, but in fact it's not being very clever at all. There are cases where a unifier might have to be clever. Let me show you one more. Suppose I want to unify a list of two elements, X and X, with a thing that says it's Y followed by A dot Y. Now, if you think of what that would have to mean, it would have to mean that X had better be the same as Y, but also X had better be the same as a list whose first element is A and whose rest is Y. And if you think about what that would have to mean, it would have to mean that Y is the infinite list of A's. In some sense, in order to do that unification, I have to solve the fixed point equation const of A to Y is equal to Y. And in general, I wrote a very simple one. Really doing unification might have to solve an arbitrary fixed point equation, f of y equals y. And basically you can't do that and make the thing finite all the time. So how does the logic language handle that? The answer is it doesn't. It just punts. And there's a little check in the unifier which says, oh, is this one of the hard cases, which when I go to match things would involve solving a fixed point equation, and in this case I will throw up my hands. And if that check were not in there, what would happen in most cases is that the unifier would just go into an infinite loop. And other logic programming languages work like that. So there's really no magic. The easy case is done in the matcher. The hard case is not done at all. And that's about the state of this technology. Okay, well now let me just say again formally how rules work now that I talked about unifiers. So the official definition is that to apply a rule, well, let's start using some words we've used before. Let's talk about sticking dictionaries into these big boxes of query things as evaluating these large queries relative to an environment or a frame. See, we can think of that dictionary. What's the dictionary after all? It's a bunch of meanings for symbols. That's what we've been calling frames or environments. What does it mean to do some processing relevant to an environment? That's what we've been calling evaluation. So we can say the way that you apply a rule is to evaluate the rule body relative to an environment that's formed by unifying the rule conclusion with the given query. And the thing I want you to notice is the complete formal similarity to the metacircular evaluator or the substitution model. To apply a procedure, we evaluate the procedure body relative to an environment that's formed by binding the procedure parameters to the arguments. There's a complete formal similarity there between rule application, and procedure application, even though these things are very, very different. And again, you have the eval-apply loop. Right? Eval and apply. So in general, I might be processing some combined expression that'll turn into a rule application, which will generate some dictionaries or frames or environments or whatever you want to call them from match, which will then be the input to some big compound thing like this. This, as pieces of it, may have other rule applications. And you have essentially the same cycle, even though there's nothing here at all that looks like procedures. It really has to do with the fact you've built a language whose means of combination and abstraction unwind in certain ways. And then in general, what happens at the very top level, you might have rules in your database also. So things in these databases might be rules, or ways to check that things are true. So it might come in here and have to do a rule check. And then there's some control structure which says, well, you look at some rules and you look at some data elements and you look at some rules and data elements and these fan out and out and out. So it becomes essentially impossible to say what order it's looking at these things in, whether it's breadth first or depth first or anything. And it's even more impossible because the actual order is somehow buried in the delays of the streams. So what's very hard to tell from this is the order in which it's scanned, but what's true is because you're looking at the stream view is that all of them eventually get looked at. Okay. Let me just mention one tiny technical problem. Suppose I'd said over here, suppose I tried saying boss of Y is computer. Then a funny thing would happen. As I stuck a dictionary with Y in here, I might get, this Y is not the same as that Y, which was the other piece of somebody's job description. So if I really only did literally what I said, we'd get some variable conflict problems. So I lied to you a little bit. Notice that problem is exactly a problem we've run into before. It is precisely the need for local variables in a language. Right? That when I have the sum of squares, that x, it better not be that x. And it's exactly the same as this y had better not be that y. And we know how to solve that. That was this whole environment model, and we built chains of frames and all sorts of things like that. There's a much more brutal way to solve it. In the query language, we didn't even do that. We did something completely brutal. We said, every time you apply a rule, rename consistently all the variables in the rule to some new unique names that won't conflict with anything. And if you look at that's conceptually simpler, but really brutal and not particularly efficient. But notice we could have got rid of all our environment structures if we defined for procedures in Lisp the same thing. If every time we applied a procedure and did the substitution model, we renamed all the variables in the procedure, then we never would have had to worry about local variables because they would never arise. Okay, well that would be inefficient, and it's inefficient here in the query language too, but we did it to keep it simple. Let's break for questions.
When you started this section, you emphasized how powerful our apply eval model was, that we could use it for any language, and then you see we're going to have this language which is so different. It turns out that this language, as you just pointed out, is very much the same. I'm wondering if you're arguing that all languages end up coming down to this. You can apply a rule or apply a procedure or some kind of apply.
I would say that pretty much any language where you really are building up these means of combination and giving them simpler names, and you're saying anything of the sort like, here's a general kind of expression, like how to square something, right? Almost anything that you would call a procedure. If that's got to have parts, you have to unwind those parts. You have to have some kind of organization which says, when I look at the abstract variables or tags or whatever you want to call them, that might stand for particular things. You have to keep track of that, and that's going to be something like an environment. And then if you say, this part can have parts which I have to unwind, you've got to have something like this cycle. And lots of languages have that character when they sort of get put together in this way. This language, again, really is different because there's nothing like procedures on the outside. When you go below the surface and you see the implementation, of course, it starts looking the same. But from the outside, it's a very different worldview. You're not computing functions of inputs.
You mentioned earlier that when you build all of these rules in the pattern matcher, and with the delayed action of the streams, you really have no way to know in what order things are evaluated.
Right.
And that would indicate then that you should only express declarative knowledge that's true for all time, no time sequence built into it. Otherwise, these things get all...
Yes. Yes. The question is, this really is set up for doing declarative knowledge. And as I've presented it, and I'll show you some of the ugly warts under this after the break, as I presented it, it's just doing logic. And in principle, if it were logic, it wouldn't matter what order it's getting done in. And it's quite true. When you start doing things where you have side effects, like adding things to the database and taking things out, and we'll see some others, you lose that kind of control. So for example, contrasting with Prolog, say Prolog has various features where you really exploit the order of evaluation. And people write Prolog programs that way. That turns out to be very complicated in Prolog, although if you're an expert Prolog programmer, you can do it. However, here I don't think you can do it at all. It's very complicated because you really are giving up control over any prearranged order of trying things.
Now that would indicate then that you have a functional mapping. And when you started out this lecture, you said that we express declarative knowledge, which is a relation, and we don't talk about the inputs and the outputs. Right,
well, there's a pun on functional, right? There's functional in the sense of no side effects and not depending on what order's going on. And then there's functional in the sense of mathematical function, which means input and output. And it's just that pun that you're making, I think.
I'm a little unclear on what you're doing with these two statements, the two boss statements. Is the first one a statement building up the database, and the second one a query?
No.
Or
Okay, I'm sorry. What I meant here, if I type something like this in as a query, I should have given an example way at the very beginning. If I type in, job Ben Bit Diddle Computer Wizard, what the processing will do is if it finds a match, it'll find a match to that exact thing. And it'll type out job Ben Bit Diddle Computer Wizard. If it doesn't find a match, it won't find anything. So one way, what I should have said is the way you use the query language to check whether something is true. Remember, that's one of the things you want to do in logic programming, is you type in your query and either that comes out or it doesn't. So what I was trying to illustrate here, I wanted to start with a very simple example before talking about unifiers. So what I should have said, if I just wanted to check whether this is true, I could type that in and see if anything came out.
and then the second one.
The second one would be a real query.
Query, yeah. Okay.
what would come out, see, it would go in here, say, with who, and in would go a frame that says Z is bound to who and D is bound to computer. And this would pass through, and then by the time it got out of here, who would pick up a binding.
On the unifying thing there, okay, I still am not sure what happens with who and Z.
Okay.
Okay, if you unify them, the rule here says, okay, so you said you can't make question mark equal to question mark who.
Right, that's what the matcher can't do. But what a unifier, what this will mean to a unifier is that there's an environment with 3 variables. D here is computer. Z is whatever who is. So if later on in the matcher routine it said, for example, who has to be 3, then when I looked up in the dictionary, it'll say, oh, Z is 3 because it's the same as who. And that's, in some sense, the only thing you need to do to extend the unifier to a matcher.
Okay, because it looked like when you were telling how to unify, it looked like you would put the things together in such a way that you'd actually solve and have a value for both of them. And what it looks like now is that you're actually passing a dictionary with the 2 variables, and the variables are linked.
Right, it only looks like you're solving for both of them because you're sort of looking at the whole solution at once. If you sort of watch the thing getting built up recursively, it's merely this.
Okay, so you do pass off that dictionary with 2 variables.
That's right.
Okay, and linked.
Right, it just looks like an ordinary dictionary.
Okay.
When you talk about unifier, you said that there may be some cases or some forms that you're not able to unify them.
Right.
Can you just, by building the rules or writing the forms of know in advance if you're going to be able to solve, to get into an unification or not? I mean, can you add some properties either to the rules itself or to the form that you're writing so that you avoid the problem of not finding unification?
Well, I mean, you can agree, I think, to write in a fairly restricted way where you won't run into it. See, because what you're getting, see, the place where you get into problems is when you, well, again, you're trying to match things like that against things where these have structure, where A, Y, B, Y something. So this is the kind of place where you're going to get into trouble. And
so you can detect it syntactically?
So you can kind of watch your rules and the kinds of things that you're writing.
So that's a problem that the builder of the database has to be concerned?
That's
or
a problem.
Querier?
It's a problem either, not quite the builder of the database, the person who's expressing the rules, or the builder of the database. What the unifier actually does is you can check at the next level down. When you actually get to the unifier, and you'll see in the code where it looks up in the dictionary, if it sort of says, what does Y have to be? Oh, does Y have to be something that contains a Y as its expression? At that point, the unifier can say, oh my God, I'm trying to solve a fixed point equation, I'll give up here.
You make the distinction between the rules and the database. Aren't the rules added to the database?
Yes. Yes, I should have said that. One way to think about rules is that they're just other things in the database. Right? So if you want to check, there are things that have to be checked that are in the database. They're kind of virtual facts that are in the database.
But in that explanation, you made the differentiation between database and the rules itself.
Yeah, I probably should not have done that. The only reason to do that is in terms of the implementation. When you look at the implementation, there's a part which says check either primitive assertions in the database or check rules. And then the real reason why you can't tell what order things are going to come out in is that the rules database and the data database sort of get merged in a kind of delayed evaluation way. And so that's what makes the order very complicated. Okay, let's break.